Hello, everyone. This is the first lecture in Calculus 2 series. Our topic for today is integration by parts. So we know, okay, so the formula for integration by parts is if I have an integral of the form u dv, then that's would simply equal to uv minus integral of v du. Well, let's see where this formula came from. So we will derive the formula. So we know from differentiation rule, this a product rule. So the product rule says if I have a derivative of the form of a product of two functions, f of x and g of x, then this would be equal to the first function times the derivative of the second function plus a derivative of the first function times the second function. So now let's take a derivative, integration of both sides. And a derivative with integral cancels each other. Then I will have f of x, g of x. That would be integral of f of x, g bar of x, dx, plus integral of f bar of x, g of x, dx. Now I would solve for this term. Then what it tells me is that integral of f of x, g bar of x, dx, that's equal to f of x, g of x minus integral of f bar of x, g of x, dx. So basically that's where this integration by part formula came from. Then all you need is basically to recognize that u equal f of x and dv equal g bar of x dx. So if you just make the substitution in this formula here, then you will get integral of u dv, and that's equal to u v minus integral of v du. So that is the formula that we got above for integration by parts. Let's take a simple example to clarify the concept. So let's say if I have a integral of the form x sine of x dx. So it's important to recognize that I will set my u to x so that when I take a derivative, this one would become of order 0. In other words, it will just become a constant. But if I take dv to be x, then I will need to integrate x. Then this one will become x squared, and that will make overall integral more complicated. So it is common sense to assume that u is x equal to x, then du equal dx. dv is sine of x dx, then v equal negative cosine of x. And now I'll just go and follow the formula. Then this integral here would becomes u, which is x, and dv equal negative cosine of x minus integral of v, which is negative, with this negative becomes positive cosine of x, and du equal dx. So now this is very simple. This one would become negative x cosine of x, and integral of cosine is simply sine. Sine of x plus c. So that is the final answer. By the way, this integration by parts is very important topic, and it has a lot of applications. So it's very, very important to understand the topic and how to pick u and dv. Let's take another topic. Sorry, let's solve another problem. Let's see. Okay, I would need to erase all this. Okay. So let's take the second example. Our second example, it's a little bit more involved. So it's an integral of natural log of x dx. So I'll set my u to be natural log of x, then du equal 1 over x dx, and dv equal dx, then v simply equal to x. And then follow the formula with vx natural log of x. So uv minus integral of v du dx. And this becomes very simple. It becomes x natural log of x minus integral of 1 dx. And this one would become x natural log of x minus x, and simply just add the constant. Okay, let's take another example. Now, this is a little bit more involved. And I would need to erase this again. Let's see. So if I have an example of the form integral of t squared e to the t dt. So again, I will simply take my u to be t squared, so that I'll take a derivative of it and I'll make the order 1 rather than 2 after taking derivative. Then du equals 2t dt, and dv equal e to the t dt, then v equal e to the t. And then, so just follow the formula, it becomes u v minus integral of v du to t dt. So as you can see, for this integral, this is also an integration by parts. Let me write it in a little bit more convenient form. This one will become t e to the t dt. Then I would need a second integration by part. So second integral by part. I'll use capital letter U just to recognize it from the lowercase u for first integration by part. Then cap u would be simply t. Then du equal dt. And dv equal e to the t dt. Then I should have used it capital V here. dv equal e to the t dt. Then v equal e to the t. And we'll substitute here. So going back here, again, t squared e to the t, there is no change to this guy, minus 2. And apply again integration by part with those, or second integration by part, is going to be u and v minus integral of v, and du is simply dt. And this one becomes t e to the t minus t, minus 2, t e to the t, and integration of e to the t is simply e to the t. So final answer becomes t squared e to the t minus 2t e to the t plus e to the t plus constant. Okay, so the conclusion here is that it is possible to use integration by parts more than one time in the problem. So for example, if I had an integral of the form t cubed e to the t dt, then it makes sense that I will use integration by parts 3 times. So this would need integration by parts 3 times. So why you don't take this as a homework and try it yourself, just to make sure that you understand the concept. I'll solve another example that involves trig function. So let's do that. Okay, almost there. Let's see. So our last example for today is integration of e to the x sine of x dx. For this example, honestly, it doesn't matter which one I choose to be x, which one to be dv, because simply derivative of e to the x will become e to the x, and derivative of sine of x becomes cosine of x. And if I take a integral of that, I'll get negative cosine of x. So basically just from one trig functions to another trig functions, and e to the x is e to the x, whether you take a derivative or you take an integral. So I would like to take u to be sine of x, then du cosine of x, and dv equal e to the x dx, then v equal e to the x. Then this one will become sine of x, e to the x minus integral of e to the x cosine of x dx. So basically, the integral that I got here, well, this also involves exponential times another trig function, which is cosine of x. So does this suggest that I need to try integration by parts for second time? So I'll take my u to be cosine of x, then du equal negative sine of x, and dv equal e to the x dx, then v would be e to the x. So let's substitute everything. Okay, so the problem that I started with is simply e to the x sine of x dx. So far it is this one, which is sine of x e to the x minus, in this integration, e to the x cosine of x is simply, I need to utilize this integration by parts, which is u and v e to the x minus integral of v, and du is negative sine of x here, which makes this one sine of x dx. So let's distribute this negative here and to the braces, and let's see what happens. Then this one would be sine of x e to the x minus cosine of x e to the x minus integral of e to the x sine of x dx. If you notice that this theorem and the problem that I started with are similar. So what I can do is that I will bring this theorem back. So I will get 2 integral e to the x sine of x dx, and that's equal to sine of x e to the x minus cosine of x dx. And now divide both sides by 2, then you will get e to the x sine of x dx, and that's equal to 1/2 e to the x sine of x minus cosine of x, and finally add the constant 1/2. So that's pretty interesting, and this is a very powerful tool to solve a lot of problems of this type. Yeah, again, this integration by part topic is very, very important, and it has a lot of topics. Yeah. In the next lecture, I would solve a few more problems just to reinforce the idea and make sure that we have seen enough examples. Looks like I forget here. This is sine of x. Okay. Thank you everyone for watching this, and stay tuned for the next lecture.